Hello, my name is John Maluli, and I'm a distinguished architect for Cisco. And today I'm going to share with you our transport slicing automation solution. So first, let's start with a quick definition of what is network slicing. So network slicing is something that actually came out of the 5G community. It's a new capability that the 5G service is targeting, and basically it is a way that from um, handset to application, the end customer gets the experience of having their own network resources. So it's a way to carve up not only the network resources, but also all of the data center resources, the radio resources, in a way that it looks as if it's their own network. Um, and it's primarily based on delivering a business level SLA, service level agreement. So the uh, the nice thing here is that the 5G community has basically defined a way to request a outcome, which is based on an SLA, which really gets into two different components: a SLO, service level objective, which is a measurable quantity such as delay, jitter, loss, availability, but then a set of service level expectations, SLEs, which are unmeasurable, but things such as regional avoidance, disjoint paths, encrypted links only, um, things that you have to kind of assume that the transport network is providing you. There's no way to really measure it or test it. Um, so this slicing capability is new for the mobile 5G carrier space. Um, but what we're going to discover is that by them doing this, they've actually helped the transport portion of the network better define um, uh, a set of virtual resources for its use, and thus, even if you're not a 5G user, customer, network, you're still going to be able to benefit from this technology for your transport use cases. So that's a big deal. Um, so really, again, for the 5G use cases, the uh, the hope is that this service can begin to bring new use cases, which ultimately drive more revenue, and things like internet gaming that require certain proximity uh, um, requirements. Connected cars is a big one. Internet of Things. So these are all new use cases that slicing is targeted at. So for the 5G use case, it's a fairly complex problem because the service actually spans across multiple domains. So you have a radio domain on the far left. You have potentially an edge data center cloud domain. You have transport domains that tie all of these things together. And then you have what's called the 5G core, which is the 5G control plane network functions that are typically in a data center. So in order to provide an end-to-end service, you need to slice all of these domains to provide some level of resource isolation. So that's network slicing. Um, Now, obviously, the transport network is only a piece of this. So the term transport slicing is used to define just the transport aspect of this, the transport domain aspect. And that's really what we're going to focus on in this presentation in terms of the Cisco solution. You also are going to hear some terms that the 3GPP community has defined around the actual orchestration elements. So for example, an NSMF, a network slice management function, is the end-to-end orchestrator. And then each of the domains has their own domain controller, which is called an NSSMF. And the end-to-end slice is called a network slice instance, and a slice within a single domain, so it's just a piece of the overall end-to-end slice, is called a network slice subnet instance. And these slices are typically built from a catalog of templates, which are, in essence, blueprints to be used. So those are called NSTs and NSSTs. So this is just some terminology to be familiar with. So again, for the end-to-end slice, which is called an NSI, it's using a slice, a network slice template catalog, and then each of the per domain NSSIs use their own specific templates, and each of these domains has their own technologies that are used to provide the resource assignment, resource reservation, the aspect of virtualization. So the capabilities that are in the transport network, which many of us are very familiar with, such as BGP-based VPNs and QoS, are much different than the capabilities that are used in the radio network or in the data center network, which are typically, cloud native functions running on Kubernetes, for example, with containers. So each domain has its own concept of slicing. And again, the trick here is to tie this all together from an end-to-end service for the 5G use case. But as I said, if we can just solve this for the transport use case for non-5G customers, then those customers will also benefit, because the same needs are there for a very simple way to reserve network resources from edge to edge of the transport network. So that's good, because it means that other customers can benefit from this concept other than just the 5G mobile carriers. So what are the underlying capabilities that Cisco is using for delivering transport slicing? So, many of these have been delivered over many years of innovation. Cisco likes to think that we are the leader in many of these. So, certainly we have a very rich set of QoS capabilities in our products. In the last few years, we've developed the concept of segment routing, both SR MPLS and SR v6. And we have a very strong suite of features and functions that are part of the segment routing portfolio, which is really going to be used for forwarding plane services for the slice. And then we have a set of performance measurement capabilities. So, it's not just enough to provision a service. You actually have to monitor it and collect telemetry in order to make sure that the service is actually meeting the SLA. We also have a path computation element and the crosswork optimization engine, which are used for, again, very intelligent path selection based on certain policies, including bandwidth on-demand policies. So this is typically, this top section of the slide are typically called the underlay features of the network. And those are then used by the overlay, which actually helps build the actual connectivity mesh of which endpoints are included in the slice. And in this case, we're using BGP-based L2 and L3 VPN technology. We are using a set of features called on-demand next hop and automated steering, which are used to BGP color the prefixes so that there's an automated way that that prefixes can get inserted into the right traffic can get inserted into the right slice depending on their destination prefix and such. So what's nice about this is that the underlay can be shared and used by multiple overlay VPNs. So there is an end-to-one potential relationship, which does improve scale tremendously with our solution. But this is pretty complicated stuff. I mean, this is there's a lot of knobs here that we make available to you, and certainly the right network engineers can go off and provision this, but we need to make it simple, and that's really what the slicing concept is all about. So really, with the slicing solution, it's all about intent. It's about outcomes, and so using declarative-based, intent-based automation technologies is a key part of the solution. You can see some of the example technologies that use declarative programming, such as Kubernetes, but this is also something that is available in our Crosswork Network Controller product via the Network Services Orchestrator. And what better way to describe intent but via models? And the models we're talking about are Yang models. And this is a common way to describe and abstract the intent away from the underlying feature knobs and basically hide the complexity. So this is, again, a key piece of the slicing solution that we're adopting from the 5G work. The IETF has been leading the effort for defining the transport portion of the network in terms of the slicing standards. There is a set of framework drafts that define the concept. And then there's also a northbound Yang modeling draft, which Cisco is participating in to help define a standard way so northbound systems can request slices from the transport network, in a multi-vendor interoperable type of environment. And this is an important point because Cisco wants to interwork with other vendors, with northbound orchestrators to fit into this end-to-end solution. And again, the drafts define the concept of the SLOs, service level objectives, and service level expectations. The drafts do not go into the underlying features and technologies required to actually implement the slice. It is a northbound facing model, which really goes more into the abstracted service intent and outcome expectation. So it's left to the vendor in terms of the building of what they call a network slice controller to actually take in that standard API and then execute on the actual functionality required to deliver the slice outcome. So really, the beauty of this is that, for us in the transport space is, again, we've had all of these features, And Cisco is the king of providing really an amazing set of capabilities, so that our network engineering's the customers who are network engineers can do whatever they want. But let's face it, it is very complex, and it is very hard to figure out how all these things work together. So what we've done with our slicing solution is by building a slicing service inside of our Crosswork network controller, a slicing automation service. We can take in the abstracted API, which again is based more on outcomes and intent, and then the controller can actually figure out and determine what knobs and what features to implement, where to actually deploy the slice, monitor the slice, and make sure it's meeting its SLAs. So what have we done here with Cisco? We've defined something called a transport slice instance, and the four legs of the table, which actually are used to build the slice instance, include proper QoS. We're all familiar with QoS policies. Path forwarding. So what is the path that the traffic will follow to meet that SLA? And we're using segment routing, traffic engineering for that. Service assurance, so several mechanisms to verify that the service is up and running and meeting the SLAs. And those three legs of the table are all defined in a catalog. So there is a catalog that the user or the slice administrator will build, which defines these parameters. And it's only done once, and then it's built into the catalog. Think of it as a set of blueprints. And then when the actual slice instance is requested, the user selects from the catalog, and then he selects his endpoints. And those endpoints ultimately form the overlay VPN that make up the connectivity for that user slice. So these are the four pieces of the puzzle that make up a transport slice. Now, it's up to the user to define their catalog entries, but in practice, we're seeing this in less than 10, maybe 20, type of quantity in terms of how many catalog entries we would see. And then out of that 10 or 20 catalog entries, the instances could be in the thousands, right? Because those are based on VPNs, and customers have different endpoints, and that ultimately defines the slice instance. So there could be thousands of slice instances, but only 10, 20, 30 possible catalog entries of different intents. Here's an example of some of the types of intents that we might see. Again, it's a combination of SLO-based intents and SLE-based intents. So these are potentially some new service offerings where we can get into things like disjoint paths, encrypted paths, where with encrypted links, we would only transit links that have MAC-SEC encryption on those links. So again, we said that segment routing, traffic engineering is a key piece of this. And by doing very granular surgical path forwarding, we can move this traffic over the nodes and the paths that meet the specific requirements. So maybe there's a set of links that have a very low latency. There might be another set of links for high bandwidth video and wholesale backhaul, which is more of a best effort service. And then we can have disjoint paths and encrypted paths. So SRTE really is the mechanism we're using to provide these kinds of techniques. It's really the only game in town if you want very scalable, um, uh, you know, traffic engineering, that is very simple and um, doesn't require, it can be based on very surgical path forwarding. So one of the other features that we have is, again, our path computation element, which works hand in hand with the optimization engine. And all of these components together make up our crosswork network controller. So these are things that are under the hood of the crosswork network controller. And you can see here is an example of how a slice gets requested and certain policies are pushed down to the head-end router, which then trigger the head-end router to then set up a series of tunnels with the path computation element. So this is how that might work. And obviously, for something like bandwidth on demand, we would be doing monitoring of link bandwidths in the network and optimizing tunnels so that bandwidth reservations are preserved. I mentioned this earlier, but one of the key features of the solution is the concept of on-demand, next hop, and automated steering. So by coloring the BGP prefixes at the destination node, BGP will then propagate those prefixes throughout the network with a specific color community. And that color community really symbolizes what treatment that traffic should get. So if it was to get low latency treatment, you color it a certain way. In this case, purple. If it's disjoint path treatment, it might be color red. And this then is a hint to the head end router in terms of how to best forward the traffic on what tunnels. So this is a key capability, and it really scales well, and it's automatic in terms of how when you recolor a route, how BGP can propagate that, and instantly your traffic can get reassigned to a different slice intent very quickly. Here's an example of disjoint paths where we have the first path up, and then a second path is requested, and then the first path is optimized so that there's no common nodes or links. And then we have a low latency type of service where there are measurements that are happening on every link, between every node. And then when a low latency service is requested, we can then basically aggregate all of the latencies across all the links to determine from an end-to-end perspective which set of links to cross to get the best low latency service. And we can even get into some more advanced capabilities, which require where we don't need the lowest latency, but we want to have a maximum bounded latency. So, for example, let's suppose we wanted to have a maximum bound of 15 milliseconds. So we don't need 5 milliseconds. We 30 milliseconds is too long, but 15 would be fine. So we could actually not take the lowest latency path, but take another path that is not the lowest latency, and it's not the highest latency. So at the root of all of this is our Crosswork Network Controller product, which is we're delivering the slicing functionality in the 6.0 release, which is shipping this month. And What's nice about the Crosswork Network Controller product is it handles orchestration of the slice, visualization, it monitors the slice, and then it verifies the SLA of the slice. So it is a complete life cycle of capabilities. The first thing that you would do as a slice administrator is you would build a catalog. We talked about the catalog, and you would define your requirements in terms of QoS, path forwarding, and service assurance. Now, this would be more of a skilled user to build the catalog, but again, it's done once, and it's typically done by a network engineer who understands the capabilities of your network and what services they could provide. Once that's done, now the actual slice instance is a four-step process, and it's very simple. You basically give the slice instance a name. You pick a template from the catalog. You then define the connectivity. Do you want any-to-any, point-to-point, hub and spoke? And then you can select your bandwidth if it's a bandwidth on demand based service, and you can then select your endpoints. In this case, the endpoints are the endpoints on your edge nodes. So you would define your node, your interface, your VLAN if you're using VLANs, and if you have a CE, a customer endpoint router attached, you can actually define a peering protocol to the CE. So you can also build your PE to CE parameters here, and you can put in multiple endpoints. These are called service demarcation points. Once you commit that, you then can you can go to the dashboard and you can see the different slices that are provisioned, and you can then click on one of those slices to get more information, where it breaks it down into the underlying components, the VPN that makes up the slice, the transport tunnels that make up the slice. So you get quite a bit of detail. If you look at the VPN service health, you will see an assurance graph which shows you all of the components that are being monitored. If you have probing enabled, it'll share with you the delay, the jitter measurements for that circuit. It'll show you the hop by hop path that the traffic is taking between two endpoints. So you can drill down and get a significant amount of detail. You can set, with the heuristic packages, you can set thresholds for things like delay and jitter to alarm if those thresholds are exceeded. So, I'm sure a lot of you guys know this, but there are three ways to provision with the Crosswork Network Controller system. The one is with the UI, very simple GUI-based UI. The other one for more of the power users are your APIs. So we have a extensive set of APIs that you can use to provision slices, and then you can also just go directly to NSO and use the CLI, including merging, pre-created files. So all three of these will create the slices, and they will be visualized. One really neat feature of the solution, and it really comes out of how our NSO system works, which is a declarative-based system, is that you can change the slice. You can change the parameters on the slice. And in this example, we're changing the catalog entry. So in other words, we're changing the intent of the slice. So you have an existing slice. It's up and running. In this case, it is based on bandwidth, which is the EMBB-based intent. And you can see in the bottom left that a certain path is taken through the network. and a certain latency of 22 milliseconds, a round trip latency of 22 milliseconds is being seen. But again, this is a bandwidth-based slice, so latency is not a requirement. But in this case, the user changes or modifies his slice intent to be a latency-based service, which is URLLC, ultra reliable low latency, and he commits that. And within a few seconds, the NSO system basically determines what's called the minimum diff of what configurations need to be changed. In this case, we're changing the BGP coloring of the prefixes. We're pushing down different policies to the head-end nodes so that the SRTE tunnels will now take a low latency path through the network. And you can see here that within a few seconds, the path changes. And now we're getting 2 milliseconds round trip. So this is really cool. This is what the cloud providers are doing in terms of on-demand type of orchestration, and it offers a whole new set of options for services that you can actually do, on-demand, pay as you go type of services, depending on what intents you select. So to summarize, the nice thing about slicing is it's based on intent or outcome. It moves us away from the underlying complexities. That is really great, and thank you to the 5G community to come up with the concept. And again, we are leveraging the IETF slicing standards that are being developed. So that the northbound API is based on intent, and but even though that we're developing to that, you still need to have all of the rich capabilities that Cisco has in our products to actually execute on the intent. And we have a long legacy of those capabilities, and most recently with the segment routing technologies, which really make this really attractive. The NSO features of the FastMap algorithm that are used for declarative-based orchestration, and so Cisco has developed the shared slices, where if multiple slices need to access a common resource, they can use the shared slice capability. We've also come up with a neat way to just create the connectivity matrix by very simple inputs of any to any or hub and spoke to really abstract much of the complexity. So again, we're delivering this in CNC 6.0, and please check it out. Thank you very much.